Thanks for everybody coming in. My name is Matt Schuetze. I'm a product manager at a little software company in California called AJUG Systems. I'm glad you all came out. I like to start usually gauging the audience awareness. Can anybody name, there are really 4 commercial companies that build Java virtual machines. Can anybody name them? Name one. Good job. Yeah, that's no fair. You worked for them. I've already picked up on that. What was the other one I heard? Red Hat's another. Two more. SAP is a derivative, so it's not really their own. Technically, Red Hat's a derivative too. Oracle's a big one. Oracle kind of is the leader. Who can name the 4th? Azul. Good. Yeah. So that tells me you've never heard of Azul, which is fine. In a couple of when Zero Turnaround and all those folks do their state of the Java industry, and we see the pie chart of who's using which JVMs, when we saw Azul claim 1%, we're like, yes, we made it to the board, finally. So in terms of overall footprint, we're minuscule compared to the IBMs and the Oracles and even the Red Hats. But we have a very interesting history and a story, and the story is about using Java in latency-sensitive environments. That's the reason the company was created. It's the reason I'm here tonight to talk about what we do. My apologies if it feels a little bit like a sales pitch. I try to make sure it's educational first. And yes, there's a product hook at the end, but I'll be honest, there's a real, I have to do a little bit of field marketing since I'm here. And speaking of that, our sales rep for the Southeast, who lives here in Atlanta, could not be here today. He fell sick. But I do have another colleague in the back row, the senior field engineer for the Zing JVM, Zing product. Evan Haxton is here if you want to wave. Hi, Evan. He's here with me all night and was willing to take questions about, how does it actually feel like to get Zing in your hands and set it up and run it and try it. And so we'll get into the details of that. Zing is basically another Java JVM. It's another JVM for servers, and the reason it exists is to remove some of the problems in regular Java that you may have hit in your lives as developers or as IT operations folks fielding Java-based applications. So we'll kind of dig into that story as this talk goes on. Oh, one more test. You passed the test on who are the 4 vendors. Who can name the JVMs associated with those 4 vendors? We're looking for actual names of JVMs. Hotspot. Good job. That's Oracle's. Mm-hmm. J9. Yep. Is that something you use?
I'm forced to use it.
Forced to use it. Okay. Red Hat's has a name that is kind of Java 6, 7-ish. I don't know that they're doing 8, but can anybody remember that name? It's called Ice-T. It's a play on words on Java. So Ice-T was their JVM. They actually backported OpenJDK 7 to 6 so that people could still use 6 for a while, because OpenJDK 6 was terrible. But that was the first release of Java that was open. And then who can name, I already said it, but one of the 2 JVMs at Azul?
Zing.
Good job. Anybody know the other one? Give you a hint. There's stickers on the back of my laptop. Zulu, yes. So we have 2 different JVMs. The Zing is meant for servers where latency matters, and Zulu is made for everything else because it's basically just OpenJDK. And so this talk is going to be about the Zing JVM. I have a slide at the very end that shows what we're doing in Zulu as well, just so to capture that we have more in our work pile than just Zing. But the story is going to be about latency and what does it feel like to try to fix latency issues in your existing Java, and what does it look like when those issues get taken away when the JVM works better? Okay? All right, so sort of the high level agenda, if you will. We want to explain the concept of jitter. And jitter is normally in electrical signals. It's a time variation in the signal that leads to noise or leads to other problems. And we're going to show how jitter in Java is not random. It's not noise. It's something else. And then we're going to see what if your mission is to actually build an application geared for low latency. I'll use latency sensitive and low latency interchangeably. I know that there's technically a low latency application crowd that is focused on running stock exchange platforms and things like that. But any application who's got to respond to requests in a short time frame, and short can be under a second, it can be under 100 milliseconds, or it can be under 1 millisecond. It depends on what is your service level for your client or your users hitting your server. So low latency or latency sensitive means my Java app must respond to stimulus in a known defined manner. Yes?
You got anything in the 10 microsecond range?
10 microsecond? That's getting down below what anything can do in software. No, I'm kidding. We're talking worst case latency. So Evans firefought several servers to bring worst case latency down below a single millisecond. 100 mics depends on your workload. And a lot of this is due to JVM behavior and also underlying OS behavior and processor and cores and tricks like NUMA and processor affinity, all that good stuff. So the people that are hunting ultra low latency talk about sub-microsecond times, and they're talking about using dedicated hardware and talking about ASICs and circuitry, not about software. So we're still trying to keep this up in a software solution running on general purpose server grade hardware, not specialized chips or code. We'll go into a little bit of the fundamental problems with Java. These are not new. They've been around since Java 2 or thereabouts, and there's tons of workarounds and code arounds. Most of them work, but they are not in the spirit of good software practice. So they actually break a lot of your well-intentioned good code. And so we're going to try to dive into why people do it and why they don't need to. Because what happens if you take away those bottlenecks? What happens if you take away the problems of the JVM, who's by nature, because it's a garbage collected, memory managed language, is going to stop every now and then to rearrange its memory structures. That's what regular Java does. Well, what does it look like if suddenly that problem goes away? And then take a sort of a state of the state of what does it feel like, what does it act like, what does it behave like to do low latency in Java in 2016. And I do have some real world case studies that I gleaned, so it's to show that it's a generic, it's a specific solution, but the problems are manyfold. There's lots of different people that face firefighting Java latency issues, and show you some examples of how they improve their situation. So I got some pictures of noisy electrical signals. If you've ever used oscilloscopes or whatever they call the IV charts on telecom signals, electronics has noise. And it's white noise, Gaussian noise. It's random signals, but it's a time variation is really the jitter. It's not amplitude variation, it's time variation. In Java, we contend that looks like a noisy signal. This is a time series of response times. It's a client hitting a server, or it's an interaction with the server application. And it looks noisy, but if you actually break this down, and we're going to spend a lot of time, I'm going to walk through what this chart is actually showing and why this is how we communicate to a lot of people what latency looks like and how it behaves. So if you study this sort of the layout, at first blush it looks like noise. It looks like a random signal. But in reality, we're plotting response time against elapsed time. So I'm hitting this server over and over and over and over, and sometimes I get really good response times. In fact, 99% of the time, I'm under fractions of 1 or less milliseconds according to that scale. It's just that every now and then I get these spikes. These spikes are a lot higher than the background. You can even see sort of a floor here that is happening recurringly, but every so often you just get these really long penalties. And the penalties happen not randomly. The penalties are actually garbage collection pauses. And when you start to look at Java behavior, assuming you had perfectly written code, you still have the JVM taking a break every now and then to free up the objects that it determined is garbage, because your actual calling threads have now have left the object references alone. You're done using those objects. They're free to be collected. The garbage collector fires, and during that time, your application is not responding. It's busy doing garbage collection. And so for the most part, this application, 99% of the time, it's running fast. It's running less than a millisecond response time. But it's actually even better than that. It's 60 microseconds. This is a very fast telco application. But the maximum pause, this long one on the outside, is 23 odd milliseconds. That's 30,000 times worse than the average case, or than the baseline case, the 99th percentile. We like to bin latencies. Every transaction, every interaction with the server has a latency. How long did it take for the thing to respond to the stimulus? So every one of these measurements shows it can be really good or it can be really awful. So the premise of tonight's talk is, well, let's dive into, well, what is the cause for those pauses? How, if it's possible, how can we eliminate them and make sure that the worst case latency is also the best case? So it's just rocket fast the whole time. Yeah?
So just to be nitpicky, which garbage collector were you running on that thing?
This is CMS. I have another slide that goes into the details. Yeah, who knows how many garbage collection strategies are in the Oracle JVM, in Hotspot? Wild guess. 3, good job. Yes, 3. Zing throws them all away and puts in a different garbage collector. That's really the basis of Zing. And we'll get into the details of that. So why? If we're going to talk about latency, we're going to talk about Java, talk about inside the JVM, talk about how code runs on the JVM, how latency is observed and measured in a JVM. Why am I here to talk about that? Why isn't Oracle or IBM or somebody else? Well, guess what? Azul is the Java vendor. We have been in the business of building JVMs for about 13 years. We started life building a server appliance that ran just Java, just the JVM. And this was something that in the heyday of a lot of VC money, they decided, hey, let's go build the biggest, most scaled out, core heavy box we could and put a JVM on it and have that be the back end of Java workloads. So the company was founded around that. We did 3 generations of our own ASIC, so it's a dedicated multi-core chip. The 3rd generation box had 854 cores and 2 terabytes of memory. It was a big machine. Had our own Debian Linux build and then our own JVM. And you still had a little client piece that you ran on another Unix machine, but the back end was running pauseless Java. Intel came out with a processor, it was the Nehalem class, that basically gave all of those cores that we had designed into our ASICs away in regular Xeons. So suddenly the reason to build proprietary hardware basically evaporated. We couldn't compete with Intel on scale of volume of processors, and to build a 4th generation would have probably sunk the company. So we made the decision to pivot at that point and take the knowledge of building that pauseless JVM, doing it on Intel's chips. So we don't have to compete against them, we just ride the wave. So now on the x86 64-bit processors, we have the Zing JVM. It's a full-blown Java runtime environment. It is an implementation of the Java SE standard. We've got versions for Java 6, 7, 8, and we'll do 9 when 9 gets a little further along. But it runs on regular Linux, on regular Intel. So you buy any Linux box, server grade, you can drop Zing in, and now you get a JVM whose job it is to keep your workload running without taking long 300,000 times or 30,000 times longer pauses than your normal workload. And we'll go into the examples that show where that matters. Where does it really matter that all of my transactions are under a millisecond or 2 milliseconds? There's actually quite a few workloads that are like that. We also, as I said, have a second JVM that's just our build of OpenJDK. That's for the generic garden variety use cases, whether it's regular work group apps or smaller servers, or now you can even put it on desktops, put it in embedded, put it in small devices. And so we've kind of balanced our company around Zing for the mission critical workloads and Zulu for everything else.
Is Xeon 5 what you're doing this time?
We are up working on all of the common Linux distributions, the RHEL, the SUSE, the Ubuntu, the Debian, Oracle Linux, and the chip class is 2010 and newer. So Sandy Bridge, Ivy Bridge. We already have some work that's going in for transactional memory on the Haswell chips that actually they had to recall or turn off the transactional memory part, but they're going to be on Broadwell. So that's the kind of grade of processor. And so, our reputation is built around low latency. So that's supposed to be the pedigree that says I should be here talking about this because that's what we do. Yeah.
Yeah, is it a specific instruction set that you guys are able to take advantage of?
We'll dive into a little bit of the implementation, but it's not a different instruction set. In fact, we use the exact same JIT compiler that's in Hotspot. It's the same emitted instructions for the chip. What we're doing is actually a different garbage collection algorithm that takes advantage of all of those parallel cores and processors. Uniprocessor Java of 1982 isn't going to cut it on a 16-way, 4x16 core system, whereas Vega was that, so our JVM is built for that. Right. Not paralyzed, parallelized. Little small difference. Okay, so let me get you, so again, I said latency sensitive, low latency, same thing for the purpose of this talk. But it shouldn't be strange for Java. So the history is, well, why would people ever try to pick a managed language for low latency? That's crazy, right? You can't trust that to be responsive at the millisecond level all the time. And there's actually people that were doing low latency in Java before Zing. And there were a lot of reasons to do it. Java is a language for which you can actually budget how long it'll take projects to run. Some of the other languages, like C and C++, the time to debug and the time to implement and the time to actually execute a project is very tough to gauge. Productivity is higher for Java because of the tooling ecosystem and all of the different options you have. So developers are typically better armed to write more code in Java than in other languages, especially native. And so these other business metrics suddenly are real. Time to have a product that works, time to hit the market with your change or your algo or your whatever it is you're building, and then also the time to get that app running at peak performance. These are all very attractive things to do Java. And of course, we can actually hire people. There are Java developers in the world. Not that there aren't native developers, but usually they're doing something special. So, Java developers are great. They can handle, as Home Depot said, the whole stack. They go up and down. And that's good. That means it's a good exchange of knowledge and skills. And so, like, our prototypical thought experiment is, if I am going to be doing something that's really high speed, like algo trading on foreign currency or even equities or something that's in capital markets, I have to design an algorithm that beats all the other players in the market so that my trades go in, and I know because of my knowledge of what's happening that if I make this trade, I'll make so a profit. But every other hedge fund and every other trader is doing the same game. It's like it's a battle for who's got the most skill to place the right trades at the right time to eke out a couple of percentage points. So if you're building algorithms that do that, like a lot of the banks and a lot of the different investment groups do, your strategy has a shelf life. Your competitors are going to try to eke you out and beat you to the trade, so you have to keep up innovating. And so they they develop and they deploy and they try different things and they see if a strategy works, and sometimes it works, but only one in a while does. So it's almost like a pharmaceutical trial. You can go all the way to the end and it still might not work. And you've put a lot of time in that, so you want to make sure that you can get changes and ideas through your dev cycle quickly. So if your business, the profitability rides on the ability to come up with new strategies, we actually have been told by these guys that they can get 2 to 3 times more code through from the Java developers than anything they could with C++. And that matters because their profit rides on the skill of the developers to come up with strategies. So they want to do it. They want to code in Java. So what is the problem? I've heard a bunch of C++ developers say, Java's slow. That's not true. It's not that it's slow. In fact, code for code, a good programmer can probably get about the same speed, raw throughput out of both languages. Of course, depends on the task at hand and if it's like for like hardware and OS, then you pretty much have a fair fight for top speed. But if you're not a good programmer, you're not going to get the best speed anyway. So it doesn't. It's not the language that's going to get you that throughput. And in both languages, both families of languages, your average or your 50th percentile of all of your traffic flow is going to be good, and your 90th percentile is going to be good. Excellent. Very as fast as that chip can go. But it's this occasional peaks, the occasional pauses, the once in a whiles that aren't fractions of 60 microseconds, it's 600 milliseconds or a couple of minutes. Those are the things that make Java feel erratic. It feels jittery because there are pauses happening, and the other things connected to the JVM are affected by that. They can feel that outage. Even if it's for 100 milliseconds, that's an outage for latency sensitive systems. And so that leads us to the story of garbage collection. The managed memory that's in Java, and technically it's in .NET, and technically it's in every language invented in the last 30 years apart from Visual Basic, not .NET, but the other one. All those languages are now managed memory to handle the fact that allocating objects is expensive and freeing objects is expensive. So how do you come up with a better system to take the burden off the developer to remember to allocate and free every object in every case in every code path? So the whole science of garbage collection is to take that burden off of the coder's hands, let you focus on business logic. Well, the GC happens in the background, hopefully freeing you of that worry. But it's also the Achilles heel. It might be wonderful in terms of some other thing in your system is helping you, but it's also got a problem, and that's pause times. And we have a whole talk. I mean, I could spend probably 90 minutes unto itself talking about the 3 different garbage collection strategies that are in Hotspot and what they all come down to. Every mode of GC in, I think, all of the big commercial JVMs, there's a new generation that's doing the fast allocation of new objects as code is running. And then there's an old generation, which is once something survives a few cycles, it realized, hey, that object's sticking around. Let's promote it to the old gen. So there's 2 different competing processes doing the allocations and the frees of memory. And every now and then, the JVM says, hey, hold on. I got to stop everything. I got to stop all these other threads. I got to stop you threads. Now I got to change the memory graph. And when I'm done, I'll release you and you can all run. That's a stop the world GC event. So the world means useful work stops as well. Your applications threads have stopped. Any clients that were connected are waiting. Hey, are you coming back? So if the new generation's job is allocating and freeing quickly objects that are born, they're used, and they die, and the old gen is the ones that hangs around for a long time and can fill up and get really big, he's kind of the cause for the big multi-second pauses. If you have lots of garbage collecting that sticks around, the rule of thumb is every gigabyte of garbage is a second of delay. So if you have a 10 gigabyte heap that needs to be freed, 10 gigabyte live set, you need to wait 10 seconds. If you have a 100 gigabyte heap, you have to wait a minute and a half. That's a long time for an application to be out of service. So let's ignore those for now. Let's just worry about the fast ones that are happening, as your code runs. They're minor, right? They're minor events. They're small, maybe 10 milliseconds each. But they happen as fast as you allocate. The goal of the new gen is you allocate and things die. So it's allocate free, allocate free, allocate free. The more you allocate, the more it's got to be freed. Those events are going to happen as fast as you use memory. So it's really going to affect your throughput. If you're worried about freeing things you're creating rapidly, you're going to have a certain cap where you can't get any faster because you're now going to be throttled by allocation and free. And so that's why you might have a good 50% and a good 90%, even 99%. But as soon as you look at the 1 in 1,000, the 1 in 10,000, they're terrible because you're waiting. You're waiting for that GC to finish the collection, and meanwhile, work has stopped. And because it also affects throughput, now you're actually, as load gets higher, pauses get worse. That feels bad to the end user. That feels like you're breaking, the application starts to feel sluggish. Load goes up, performance gets worse, people get angry, people file IT tickets. If you're actually doing expensive things like trades, now you've lost trades, your risk has gone up, your profitability, and the overall expectation of your service suffers. So our contention is those little spikes, even this floor, the 5 milliseconds to the 10 milliseconds, they're bad. The big ones, yeah, they're really bad too, but I mean, you are cutting out what is otherwise good operational code, and it's a flaw in the JVM, what it comes down to. That's our opinion. And so all of those, even anything that's above the green bar, which is where 99% of the traffic is, anything that's on that chart above that is a stop the world pause, and it's a problem. So what? So now you realize, my JVM's pausing, what do I do? The common answer is don't talk about it. This is something that if you are aware of it, you're like, wow, I have a potential problem here. My app that I think is running okay is actually suffering. It's just suffering at a small scale. Or in the case of old gen, a very large scale that you can actually feel. But honestly, there's been a whole bunch of the people that we've talked to are like, it's too hard a problem. We don't want it. We're going to live with it. We're going to live with it. We know we can't reach a certain level of throughput without seeing this problem. So we're going to just put a bunch of servers in parallel and add more hardware, and that'll be fine. The problem goes away if you scale horizontally. Well, that's another problem. If you just sweep problems under the rug, eventually you're going to need another rug because you're avoiding taking the problem at its root cause, which is the JVM is taking a nap. So in the world of finance and in e-commerce and in a lot of clothing retailers and a bunch of people that they want to have very fast performance all the time, what were they doing, or what would they do to avoid GC? And we have a term we call Java, which is air quotes Java. You're not really writing Java, you're kind of writing C in Java. It just happens to be using a JVM as your place to do it. And they avoid any allocation during runtime. They pre-allocate everything. And therefore they're building their own pools for objects, kind of like you would if you're doing something in C again. And they have to write every line of code themselves because they have invented this memory model that avoids normal GC. But that means they can rely on no third-party code. They can't just grab some framework from Apache and plug that in. They have to write it themselves. And anybody else they hire has to learn their discipline about where and when you're allowed to new an object anywhere in their app. And suddenly, all of those great things about Java we talked about before are out the window. You're coding natively, just happen to be doing it in the Java language. So what Java meant and what it allows is now greatly diminished. So from a vendor standpoint, we think there's evil in marketing, and it's kind of like the fine print in a legal document. We guarantee a worst case of 5 milliseconds 99% of the time. If you ever see that written on something, you should raise the hackles on your neck, because if it's great 99% of the time, well, then it's fine, right? Like, no, the 1% is going to blow that 5 milliseconds out of the water. We saw that. We saw 30,000% degradation. The other thing about JVMs, or GC cycles, it's mostly concurrent and mostly incremental. Well, what are you leaving out? You're leaving out that it's, at sometimes, the JVM's taking a nap. So another one we love is fairly consistent. Is it consistent, or is it just fairly consistent? And then typical pauses. Well, tell us about the atypical pauses. The atypical ones are the ones that bite you worse. So we've seen this. We've seen in the global banks. We've seen in a couple of e-commerce companies that the Java developers sit down and they go ahead and they're going to do the no allocation type code. They're going to write their own object pools, and they still see pauses because you can't escape the new gen. And you might get fewer of them, as in they're not as often, but you got fewer people that know how to do that, and you have to write it yourself to get there, and you wind up debugging malloc and freeze patterns, those same sort of things you'd have writing in native code, and they can only rely on memory certain ways, and it's no longer fun. I mean, you're basically putting band-aids over something that is a fundamentally problematic issue, and you're doing everything except addressing it head on, this is the fundamental problem. Any stop the world mechanism, anything that stops the Java threads for any purpose, it doesn't have to be GC, for any purpose, anything that stops the Java worker threads fly in the face of low latency and low jitter. You have to do something to get rid of those pauses, to stop the world where everything goes. If you have any other tricks in your bag as a JVM writer that reduces the pauses that the working threads feel, I don't care how you do it, pixie dust, magic. If you can take the stop the world events away, you'll get to the low latency realm, and you'll get to where things run full bore without the naps. When we discuss this with customers, we always want to say, so you're trying to reach a certain throughput. And we already said that if you go too fast, you allocate too fast, you free too often, the GC starts to throttle you, you start to feel those pains. So what is the throughput that you can maintain? You want to go fast, but you don't want to go so fast that your pause times break your response time envelope. We call that sustainable throughput. Can you sustain this rate of allocation and sustain this rate of GC safely? You're not introducing pauses that break your response time rules. And so here's a picture of something that had wonderful throughput, but it wasn't sustainable. Imagine crashing your Ferrari. You can go 100 miles an hour, but every quarter mile you hit a pole. You can't sustain that throughput safely. You have to bring it back down so you can actually run without wrapping your fender. And once you've hit a pole, like you've hit a pause, it doesn't matter how wrecked the fender is. It's stopped. It's not going anywhere. You have to have a way to avoid poles. So that's unsustainable. Our belief is that stop the world events in garbage collectors are, we called it once the Achilles heel. We think it's an industry-wide problem. We think there's been a lot of science that's gone into garbage collection, but how long did it take for G1 to come out? It shipped in 7 U4, I think. So it's been now in the market for 3.5, 4 years. Not a lot of adoption. That was after about 8 years of development. So building new GCs is a hard thing. This is a problem that's in every JVM, that if you're trying to do latency sensitive work, you will hit this problem. Well, it was an industry-wide problem. That our contention is in Zing, the way we've structured garbage collection takes GC pauses off the table. And it gets back to what we said about that big 800 core system. We're moving garbage collection off of the CPU cores that are running your actual Java workload. We're running them in parallel. The magic then is, how do you make sure that the running threads can go as fast as possible through allocation and GC without accessing objects that are in motion. You know, if you've compacted your heap and you've moved an object from new to old or from old to some other space, how do you make sure that that Java thread always sees the right object when it's referencing it? If you watch the old object and it already moved, you've got stale data. If you went to the new object and it hasn't moved yet, you've got some other bizarre data. So it's keeping references to objects accurate in the wake of high-speed motion. That is the secret sauce, if you will. So if you were to actually like go to the JVM conferences where we talk about this stuff, the wording is, it's a monolithic stop the world new generation. So new generation fills up, time to GC, we pause the working threads, we collect anything that's garbage, get rid of it, all the way back down to where you have only your live set left, and then you release the threads and let them run again. That's the way the new gen works. So they're small because the space is usually constrained, maybe a gig, maybe a couple gigs, but you're filling and freeing and filling and freeing and filling and freeing, and it's pretty quick, but it's linear with allocation rate. And it is definitely a stop the world pause. Your working threads are stopped. All the teams, the J9, the hotspot, the ICE-T, all of the science of GC is now working on that old gen. What happens when I build up all of these old objects, how do I get rid of 30 gigs, 50 gigs, 100 gigs of heap without that pause penalty? So G1 was about that. The balance collector in J9 was about that. It's all about taking the time to free objects and either chopping it up so it's small pieces of levelized time so that each pause isn't so bad, even if you get more. That's G1's answer. Or it's trying to do things in a concurrent or even parallel way, but at some point when stress gets high, they fall back on stop the world, and that's where we fall under the word mostly or fairly. It's consistent until it's not, and usually when it's not is when you've gone beyond what is sustainable. So the design of Vega, and therefore the design of Zing, is based on any stop the world GC pause is considered illegal. That is the primary goal. Get rid of stop the world GC, and that was the design basis, and that's been our focus. So even the short pauses are considered bad. Design them out of the system. And if you are able to do that, now suddenly a whole bunch of things are no longer tied to memory size. If you can sustain a transaction rate or a user count because the GC free always keeps up with the GC alloc, and there's no penalty against your Java threads, you can do a lot of really good things. You can have either very large heaps or you can have very fast small heaps. But the goal and the result is those periodic pauses fall out. And if you don't put a stop the world fallback in, it can never happen. So that's the design of the Zing garbage collector. It's called C4, not like the explosive. It is continuously concurrent compacted collector. So I'll go into what that means. Concurrent means it's happening at the same time as your Java working threads. The active GC of freeing objects is happening on a parallel core or processor. It's compacting, meaning once you've allocated a bunch of objects and your logic has decided which ones of those are no longer being referred to, so those are garbage, it will compact the live objects and treat everything else as empty space again, so reuse it. So the way Zing works, it's got two different concurrent compacting collectors. The old gen for the longer range, longer duration objects, and the new generation. So even the short pauses are, effectively removed. And there's no fallback. This is the way it works. The new generation is always compacting in parallel, and the old generation, and they're not even coupled. They just go as fast as they need to go for the allocation rate. So why? Great, you took away the pauses. What happens? Well, so this gets back to the idea of responsiveness. How responsive does your server need to be? And can your server, if it's no longer got this choke point where a pause might jump up because of a fast allocation, what's the benefit of that? Well, here's an actual real world example. Data's not that new. I think it was a year ago, January. But one of our customers, who actually is very open about their use of Zing, is a foreign currency exchange trading platform in the UK. They're called LMAX. Their team invented the framework called the Disruptor lockless queue framework. So Disruptor is part and parcel of the exchange infrastructure that they wrote. And this is an event that happened. I don't know if you can see. It's foreign currency is, you're doing currency swaps. How many euros can I buy for $1? And usually in, orders of millions of units exchanging hands. And this particular currency pair was the euro against the Swiss franc. And at about 11 in the morning, the Swiss central bank made an announcement about, the value, ultimately affecting the value of the Swiss franc. And the LMAX exchange witnessed this event. Traffic spiked to 7 times its normal level without any warning. And traffic stayed elevated for half an hour after that news broke. And despite that, without any warning, without any change to the system, any new, throwing extra hardware at it, Zing kept up without any pauses. So it took a 7 times the normal hit, and they rode through it like no big deal. No, any other exchange that had stop the world thing and where suddenly traffic is 7 times higher is going to say, wait, whoa, hey, whoa, hold on, let me GC. It didn't. It just kept right on running. They saw no ill effects during something that was normally, a very disruptive event. And the other thing they told us, which is probably more interesting, is if you actually look at everyday traffic on their exchange, now like we're zooming in with an oscilloscope, looking at every individual millisecond within a second, this is what their traffic looks like. It's not constant, it's not average. The traffic itself bursts. Every quarter second, somebody's algorithm is hitting that exchange. You can see 4 huge spikes at the first millisecond, the 250th, the 500th, the 750th, and it repeats. And every 100 milliseconds, or I'm sorry, every 10 milliseconds, you see another beat. So there's people hitting this service. I guess that's 100 milliseconds. Every 100 there's a peak, and every 250 there's a peak. This is the algorithms fighting each other for supremacy on the exchange. And what it means is everyday traffic itself is really 7 times the average. You cannot use averages as a way to talk about transactions that have to respond fast. If it were, they'd have 1/7 the need of hardware or software on their exchange, but the real world shows otherwise. The real world is not averages.
Just for anybody who doesn't know, I met one of those guys from LMAX a couple of years back at the Java Posse Roundup, and there's a couple of talks on the LMAX and the way they do their source code. It's actually really worth watching. It's some pretty crazy stuff they're doing.
Yeah, we've actually done a couple joint presentations with Mark Price of LMAX, I've got a deck if we want to look at what we basically did this and a bunch of other explanations of how their exchange works, and it shows packets moving on through the gateways onto the matching engines, back into the secondaries, back through the matching engine, back out to the market. It's pretty fascinating, and they are an example where they started off with a very highly engineered system. So they got their pauses down to 4 milliseconds every 30 seconds. Sorry, let me say it again. Yeah, they were already, very, an exchange is not just one big computer. An exchange has got ranges of functions. The matching engine is the thing that says, does the price you are willing to bid for this security match what I'm willing to offer? So the matching engine has the job of seeing, do bids and offers match? But the gateways and the risk and the market data feed, all that is connected. It's a very latency, it's the most latency sensitive system that we see. And they put truckloads of engineers to make sure that every flaw, like they use high-end networks, they use high-end servers, they use Java, they use usually real-time Linux OSs. Their goal is latency, to get it down to very fast, because people have the ability to go to a different exchange and trade currency pairs. They're trying to be the better exchange. But anyway, so I digress. They took 4 milliseconds every half a minute down to 1 millisecond every 2 hours. And that's after they'd already put in hundreds of man years of development time in that system. They were still able to get that much of an improvement. And on these other systems that were, well, that's not really the core, but it's still part of the exchange, 50 milliseconds so a much longer pause every 30 seconds, down to 3 every 15 minutes. So the pauses that are there are not GC, they are something else. You're still going to always have some pauses. The question is, how often and how small can you get them? And this is what they did after doing a trial with our London team. And what they found after doing this cutover was, after using the CMS, which is probably the most common throughput-oriented GC mode in hotspot, they had these once in a while, half a second pauses that were inexplicable. They're gone. They don't happen anymore. They also found that on something that was at the back end of the market system, like the risk engine or the market data feed stream, if it had a problem, even though it wasn't on the fast path through the where trades are executed, if that had a pause, well, suddenly that could put back pressure on the high latency or the low latency system. So by improving that, even though it's a non-critical server in the grand scheme of things, it took away those other mystery pauses on the critical path. So those were, again, not predictable. They would happen a couple times a week, and people would just shake their heads like, oops. And the oops in this case could be lost trades, very significant lost profitability. It's not a theoretical thing. We are putting Zing into places where the goal or the mission of that application is to take pauses away and make the code run screaming fast without taking naps. And we say it's not just theory because we actually help a lot of people measure the latencies in their applications. A lot of Java profilers are geared towards finding CPU consumption in a thread or in code, or maybe wait times if a piece of code isn't running or if it's swapped out of the processor. But it can't often tell you what's happening in the JVM itself. And a profiler like a profiler, just like a Java worker thread, may be paused during a GC as well. So a profiler does not necessarily help you find things that are in line with the JVM itself. So what we have is a little tool, pretty simple. It's called JHiccup. You can run it on any JVM. It can be on J9, it can be on a hotspot, it can be on Zing. But the point is, measure the milliseconds every millisecond. And if you were able to service the call within that millisecond, great, nothing paused you. But if anything took longer than that millisecond, something in the JVM caused a pause. And so let's actually capture what those pauses look like. Let's graph them, which is what the top chart shows. It looks like the one we saw before. Let's see what their impact, what their magnitude is, how frequently they happen. And then let's do something else. Let's take those hiccups, those pauses, and let's plot them as a histogram so that we can actually talk about percentiles. If you come away with anything today, just remember this. Java behavior is not random noise with a standard deviation around an average. It's a phase shift from the threads are running to the threads are not running. And the question is, how long were they not running and how frequently were they not running? These histograms are showing a zoom in, we called it a high dynamic range histogram, where we are intentionally showing you the 90, the 99th, the 3 nines and the 4 nines, because that's where the evil is. That's things that are happening frequently enough that they are affecting your system, but not so frequently that if you plotted it on a linear scale, you just have a big line. It doesn't give you the dynamic range to really study how often things are happening, because they're happening at different rates. What you can see in this chart, hopefully you can make sense of this. The time series is like we saw before. There's a series of very frequent 400 millisecond pauses, and once in a while there's a 1.6 second pause. I think this was it's a telecom application. The histogram then shows the same thing. The max is still the max. The 1.6 seconds is the worst case. That happens once every 10,000 transactions. But you can see everything keeps up until about the 92nd percentile. There's a shelf here and another plateau up there. Turns out these are new generation pauses and these are old generation pauses. And the stuff in the middle is what we call mixed mode, where you're starting to see the effects of both together. So we like to do a lot of these plots because it shows us when we go into an account that's trying to remove pauses, we say, all right, here's what you got today. Let's set up Zing and look see if it got better or worse, or is there anything else we can do to make it meet your target? And so here's an example of a specific low latency application. You can see from the graph, it's already very fast. Worst case of, I think this might be the one that we started off with in the opening slide. Worst case latency of 23 milliseconds, pretty quick. 99 percentile is down below 1 millisecond. And you can see the break in the curve is at 99. Okay, so this is where you start to see pauses. And, so pretty clean, ultimately. But when we dropped in Zing, you think, well, okay, I still get sort of a noisy chart up top. I get kind of the same break of a curve on the bottom. I see more pauses out at the end. But who can tell me one thing about these graphs that should jump out at you? It's the y-axis scale. The scales are different. If I plot those on like-for-like scales, Zing doesn't even appear because everything is below a max outlier of 1.5 milliseconds. For the same load, the same hardware, same application. We just changed the JVM. So the big outliers are gone. The very fast new gen are gone. Now you're left with pauses that are happening, but they're probably not GC. There's something else. And there are things after GC that affect application behavior. There will always be pauses at some level. The question is the level below your mandate or your requirement? So that's why we talk about requirements. What is the goal of this application? If you know that you have requirements, you have a set thing where you've talked with your business owner or your client, your customer, that says, I will tolerate an average latency of 30 milliseconds. That's fine. Never break that. But I know that in a real system there are pauses. So 1 out of 100 or 1 out of 1,000, yeah, sure, you can do 100 milliseconds, but never ever break 100 milliseconds. That is not acceptable. So that's how you cast requirements. What is the baseline workload, and then what is the outliers? What are the allowable outliers? This chart breaks the SLA. There are too many pauses above the requirement, so it fails. You have to do something to that system to bring it back within line with the SLA or with the requirement. And it might not be called an SLA. It might be just called like a non-functional requirement. It could be given to you as in different terms. But you can't just say, I have one number. If I said, I want this to behave fast, it's got to be better than 100 milliseconds, I could let this go like, okay, so every transaction will be 100 milliseconds. No, we want it fast. Well, then I'm going to let some transactions run, that'll take a minute. No, that's not acceptable either. So because these spectrums are like that, the discussion's got to be about what is the base case and what are the outliers, what is allowed in each situation. So when we talk about real requirements, we say, well, tell us what they are in terms of the percentiles. What is allowed up to 99? What is allowed up to 4 nines? And what is the max? What is the level at which it is just not acceptable for this workload? And so we wind up doing multiple curves with multiple conditions. Either change the JVM or change some affinities or change something about the Linux that's underneath. Try to figure out a way to meet the proscribed requirements. And this is a good one that gave us 3 breakpoints, 99 and 4 nines. So getting back to, okay, what is the requirement of an application? Requirements are different. Your application might not be the same as LMAX running on foreign currency trades. It could be the same as like an e-commerce app, and I have another example about a situation like that. But having the discussion with your stakeholders about what is the allowed latency for my system, and how do I plot that to show you I'm either meeting it or I'm breaking it and we have to go do some sort of remediation, that's the discussion that JHiccup lets you have. So, 25 milliseconds is pretty aggressive for most garden variety business apps. 100 milliseconds isn't. 100 milliseconds you can see with the naked eye. So, there are things that you can start to notice as a software user. So this is an actual portal application, like a web portal type setup. And this was another bake-off, Oracle Hotspot CMS against Zing. And it's not even it's not that big. It's only a gigabyte heap, a gigabyte live set in an 8 gigabyte heap. That's common for software vendors to say, yeah, set XMX no higher than 8 gigs. Above that, starts running into pause problems. We hear that a lot, 8 gigs, maybe 10, 16 if you're pushing it. But let's say this is just, 1 gig live set and 8 gig heap, pretty common. The curves look the same. They both have the spikies every now and then. They both have the histogram that shows really good behavior up into the 90s and then starts to tail off, break as you get into the higher latencies. But again, same problem with this chart. They are not the same y-axis, and they are therefore not the same max violators. If you plot like for like, Zing doesn't even appear because the latencies are all down at the origin. If we go back, we see that the max latency for Zing was 20 milliseconds versus this other same software, just a different JVM, 13-second worst case. And it's happening every often enough that it's visible. It's only a 3,500 second run. It's already happened 4 times. So, it might not happen frequently, 1 in 10,000, but it's happening, and that's a long time to sit and wait. 13 seconds for an application. I don't care what portal you're sitting on. You don't want to be behind the UI that's hitting that. So here's the last e-commerce case that might be applicable. Guy from Home Depot's not here, but this is sort of up their alley. An actual web retailer powering their web servers on Java. And their case is very relatable. It's Cyber Weekend. Their case was, hey, we're facing another Thanksgiving weekend. Cyber Monday is actually moving forward in the calendar. It's not Monday anymore. It's actually starting on Friday and even on Thursday now. The sales start before dinner's over, Thanksgiving Day. And web purchases are getting higher year for year. So you can sort of see that the trends are more people are shopping on Thursday, Friday, Saturday, Sunday, Monday, and you have to be ready because the load on those 4 or 5 days is unlike what it is for the rest of the year. If you actually scaled up to match your peak load, you'd be investing a lot in hardware and software that only gets used on those days. You can see that spike right there, and it's funny, even the intraday, dinner's over, let's shop, it goes up. So those are the sorts of real world traffic that you're trying to contend with if you want to have a responsive, reactive portal. In this case, e-commerce shopping site. So, the e-tailer is based in Salt Lake City. They told us, we see spikes from Thursday to Monday. They did a release of their site where they added a product gallery that's based on Solar or Lucene, like the search components. And so they know that the surge is big, but when they added this gallery search, the GC times were crazy long. And they knew that they had a higher footprint, but the impact of having a very sophisticated data set now live meant that the GC times were, if anything, worse, and going the wrong direction. So they actually found us on the web, read about Zing, and they actually came and talked to us at a trade show in San Francisco. Figured out, yeah, maybe this will work. Let's see if do an actual pilot test, see if it works on your workload. They run Amazon virtual instances, so cloud-based. And other than needing one little tweak to Linux, and we usually have about 2 or 3 different things we want to set in Linux, like turning off balloon driver and say the other one for me, Evan. The other setting on Linux, transparent huge pages, turn that off. Typically, those are 2 of the tweaks you might want to do. But otherwise, it's the same OS, same hardware, same Amazon deployment. Oops. And they left one of the nodes running Zing while the rest ran their ordinary hotspot. And lo and behold, they got better profiles. And they didn't have to tune anything. They just set it up the first time, and it just works. So the rollout took a little bit longer, but they wound up putting it on all the different Amazon nodes, and it was completely stable. They'd never had a Thanksgiving where they got through the whole weekend without some last-minute jockeying to get either more hardware or more software working. So they were thrilled with the results. Because tuning a GC, if you're either in development or you're in operations or you do DevOps or whatever, it's hard. It's not easy to set all the different modes and thresholds and ratios in the 3 stock GC engines that are inside of Hotspot. And why is it hard? Because they give you a lot of tuning knobs, a lot. The parameter space is like several dozens of terms, and so you wind up with JVM switches that kind of get crazy. And this is one example. You've set a heap size of 12 gigs, but now you've controlled every factor and ratio about the new gen and the old gen. And, well, no, that wasn't good. Let's try it again. We'll try a completely different set of switches. And by the way, this is the exact same application. They just tried different ways. It's trial and error to figure out which are the ones that work best. And if you don't know what the survivor ratio of 128 versus 2 is, that's like a world of difference in behavior. So that's the kind of things you have to either pay a Java consultant to come in and spend a week of your money to figure out what is right for your workload, or you have to become an expert in GC tuning and read the garbage collection handbook and hang out with guys like our CTO who this is what they like to do, to really know this at a visceral level. But there's so many switches. We got an estimate that if you really wanted to examine all the GC switches between going from like a Java 7 to a Java 8, you'd have to really understand about 300 different terms and know what the behavior is. And if you actually were going to test them, that's an infinite test matrix. So either you get lucky and it works out of the box, or you're stuck, diving into learning GC science. Not that that's bad, But if you're doing that, you're not doing new development. You're not doing things that the business needs the application to do. You're basically just trying to make it work, and not always something you can do once and forget about. You do it every time a workload might change, or every time the source code might change, and you have the potential that you have to go back and tweak a switch.
Question. So basically, let's say you solve the problem. Are there any like drawbacks to the way your engine works? I mean, I'm just trying to figure out.
There's
so,
one.
So basically, if you solve the issue, but yet other multi-billion-dollar companies that are developing Java for many years,
Right. So there are pros and cons. We'll get to some pros and cons in a second. But in terms of setting GC tuning variables, Zing doesn't offer many because Zing is adaptive. There's only one variable for tuning GC, and that's heap size. All you said is XMX. So your application might need 8 gigs, it might need 20, it might need 40, it might need 60. That's all you said. Because if we go back to what we were talking before about continuous compaction, the JVM knows how fast you're allocating, therefore it can know ahead of time how much it needs to free. That's part of the design of the GC. If you can accommodate enough space that your free has enough, I guess, wiggle room so that no matter your allocation rate, your free can keep up, you've got 80% of the problem licked. The other part of the problem that you have to deal with is where I was talking about where objects have moved, always landing on the right object and not getting obsolete data. And so those two ingredients are at the heart of the Zing algorithm. And there is a penalty. Here we intentionally put 8 and 12 gigs in the last slide and 40 here. It might be a higher heap, so it might cost more, static memory for Zing to run the same application as another, like for like. It's not going to necessarily fit in the same space. If you only have a 100 gig server and you're using 90 gig for your heap, well, it's probably not going to be big enough for Zing, who might want 120 or 140. It's, call it 20 or 30% tax on total memory. So there's one. But presuming GC is solved, and from our contention, our design is it's good enough to have survived now in the market for 10 years. Well, the design's 13 years old, but Zing is actually doing better in the market now because G1 can't keep up with what its intentions were. So, and then something like JRocket, which was a JVM that was supposed to be time-bound, time-sensitive, it can't even touch what Zing can do. So, I mean, it's like it's apples to cars. It's a different conversation. And I'm a little biased because I work for the company that makes this stuff. But just seeing the values and seeing the numbers and seeing the change in behavior just from a stock install, it's great. If you really want to get down to the ultra low latency stuff, you're tweaking Linux OS variables, not JVM. So it all again gets back to what are the requirements for that application. But if you go beyond if you go beyond garbage collection, let's say there are no more pauses due to GC. Well, what else is there? There's actually a whole big world of work in compilers, because inside of the JVM, not only is there memory management, but there's also the jitter, the JIT, not jitter, but jitter, that is JIT compiling your Java bytecodes into machine assembly. And so there are trade-offs all the time when you're building a JVM, speed versus outliers, memory versus CPU. Where are you going to cut corners to be able to make one other attribute better? And honestly, for Zing, the focus is always, you can make the presumption you're going to be running on a multi-core, multi-socket, beefy machine. It doesn't have to be the same JVM that works on a laptop or an embedded. We just know that. It's designed to be a workhorse. But, to be able to get rid of those outliers, there are some other costs that you have to look at. We talk about bias locking, or we talk about loop unrolling, sort of the things that go into the compiler side. Those are two things we focus on. A big one that we've spent a lot of energy trying to understand and rectify is something called de-optimization. The whole concept behind hotspot the term hotspot is while an application is running, keep tabs on how many times methods are called. If they're called very frequently, that must be a hot path. Let's put that through the JIT compiler. If it's called even more times, that must be a screaming hot path. Let's put it through the optimizing JIT compiler and get really good long assembly chains, optimal code. Take longer to do the compile, but figure out what is, for this workload, what is the best way to create the machine code that's ultimately going to run. The problem with hotspot is if it decides, well, I used this optimization strategy before, but now I see that's not the real world traffic, I'm going to redo my optimization. Well, the JVM will basically stop, throw away the compiled code you had, fall back to interpreted, catch back up, and recompile in an optimal, re-optimize for the new pattern. That de-optimization from, stop, back up, fix, go back forward is another type of pause. And these can be deadly, both at the beginning of a trading day, if you're on a trading platform, or late in the day when traffic shifts and suddenly now your JVM is stopping to recompile code when it should be running. So that's a whole big world of science. Has nothing to do with GC at all. Lock deflation, weak references, soft references, safe points. Safe points are, in JVM speak, any time a thread does have to stop to allow changes to the memory graph to happen, that's a safe point. So it can happen inside of methods, usually method enter, method exit, back edges of loops. Those are times where the JVM is going to be working. It's going to be moving objects around, but the worker thread does have to stop. But the stopping point is not a long GC pause where everybody stops. It's one thread stopping for a little bit. So we consider time to safe point, time for threads to come to the point where they take a little break so that we can shift memory they see. That's our next bogey to solve or to reduce, to keep the time to safe points down. And in regular JVMs, a lot of save points use a global mutex or a global save point so that all threads have to come to a halt before it's now safe for memory to change. And so like GC phase shift deoptimizations, class unloading, thread dumps, lock deflation, all of those things cause a safe point check or a checkpoint. And the question is, which thread causes the delay? It's not the fastest thread to reach the safe point, it's the slowest. So whatever is the slow thread to get into the that checkpoint it's the same problem you have with multiprocessors, Amdahl's law. Just throwing n processors doesn't mean your workload's going to be 1/nth the time to complete. And many of the code paths in the JVM are long, so are subject to safe points. So we've put engineers and time into studying how to make safe points safer. And we actually have a safe point profiler built into the JVM so that we are keeping tabs of our own safe points. And that also leads to our CTO walking around smacking developers because our internal goal is 55, half a millisecond. I think there's an internal goal of 55 microseconds, but the real, if you ever see anything that's more than half a millisecond, we have people that want to know why. So now let's assume you take both GC and time to safe point off. Well, what's left? You're below the JVM again. You're down into the OS. And scheduling pressure, how many threads you have fighting for time on cores. Hyperthreading on Intel processors. It can be good, it can be bad. Anytime you have disk swap, a lot of really ultra low latency apps, you're not allowed to swap the disk. It's basically turned off. You cannot have the OS deciding I'm going to swap in huge chunks of pages just for kicks. Power management, any throttling of CPUs, that can introduce timing jitter. And then the thing that's in Linux, transparent huge pages. The third ingredient of Zing that makes Zing powerful is we actually do drop into the Linux kernel a kernel mode object, and that kernel mode driver, for lack of a better term, does page management. So we don't want to use Linux's transparent huge pages. In fact, most JVMs and databases think transparent huge pages are a bad idea, but the Linux kernel community won't adopt our approach, so we are stuck putting in our own driver and just leveraging that. But the idea is, well, instead of using 4K or 4 meg pages, let's use huge, use our own pages. And so that gives Zing the ability to not only allocate quickly, it's basically got a pre-allocated buffer sitting in kernel mode anyway, and that so he can switch pages really fast. So there, I gave you the three secrets. The three secrets to Zing: kernel memory driver, guard. What are they called? Basically, guarding references to objects by having a pointer to the object as opposed to the object itself. I think in the literature those are called Brooks pointers. And then the third one is, everything is parallel. Everything is running on opposite other cores. So just to wrap up, this was a lot. Hopefully this was interesting. The idea is you can actually stick with Java and still do low latency work. GC is not the dominant issue in Zing. There's something else behind it, but usually we can get down to a couple milliseconds out of the box. Nothing different than changing your Java home from one JVM to another, and actually removing some of the switches that you had for other GC, because we only really need the heap size. Very doable, get down below a millisecond if that's your level. We've got banks and other shops that are doing sub-millisecond work. And the special code arounds, the special duct tape all fall away. You can just use Java. You can use the open source things you pull from Apache or from a commercial vendor. You can use as much memory as your system can hold. We just did a release of Zing to market in January that can do 2 terabytes of XMX without pause penalty. If it was a regular JVM, I said a gigabyte would have been a second. That's 1,000 seconds. You'd be sitting around for an hour. Well, a couple minutes anyway. And if you're good in Java, you stay good in Java. You're actually still writing Java code at the end of the day. So we call it the cure for the Java hiccups. Okay. Now, before we wrap, I promised, I'm trying to. This is trying to be educational. Trying to take you into the world of what low latency means, how you measure it, how you look at it, how you talk about it, how you reason with it, and then what are your recourses. We of course would like you to take a look at Zing if it's something you'd be interested in. There are pros and cons. It's not a free open source download. Zulu is free, but Zulu isn't Zing. Zing is it's a server grade commercial JVM. We have a direct sales force and field engineers like Evan that will come help you get it set up and make sure it works in your environment. It's a subscription model. It's actually, we don't count cores, we don't count sockets too much. So it's a very easy way to get spun up and try it if you're on a critical application. And if it's something that's right for your organization, it's probably worth giving us a call. But I wanted to explain, this is my actual marketing pitch for Azul. Now that I've given you all the details about Zing, everything I know about it and what it can do. But I just want to give you a point in time pitch for everything that we're doing, just so you know, when someone asks you next time you're in a JUG meeting, who's the 4th Java vendor, you'll know more than you did when you walked in. And so these are the things that we consider our hot topics. This is what Azul, the brain of Azul, is thinking about in 2016. First off is our 2 terabyte solution. That is live, it's GA, it's downloadable, it's usable. You could, if you ever wanted to see, a 1.6 gigabyte heap running, we've got customers and partners that are doing that now regularly. We finally were able to figure out how to put Zing, which is the JVM and then the memory driver, into a Docker instance. So still have to have the memory buffer down in the base OS, but you can put ZVMs or JVMs in Docker instances and move them around from host to host. So that's both for on-prem or if you're going to go public cloud. That's now live. We finally added a JMX, real JMX plumbing in addition to standard JMX, because a lot of times people said, well, hey, I got this great JVM, but I can't monitor it using my standard tools. The problem is JMX for memory is designed around hotspots GC, not Zings. So we finally had to add our own custom, our own extended JMX MBean or MX Bean to show GC and to show pause times and to show the things that matter for Zing. But it's JMX, so any collector can see it and graph it. And we're always focusing on performance. So performance. Every release, it's one of our common themes. We are sensitive to the fact that workloads are moving into the cloud. So we actually have Zing available in the cloud today. You can go buy time on an Amazon machine image and basically pay by the hour like you do for VMs on Amazon. It's just you get Zing pre-installed, ready to go. You can drop your workload on, run Java, run your server app, and if it works for you, then great. You can deploy it on Amazon, or you can give us a call and we'll talk about bringing it in-house. And we also have proven that we work on Rackspace, and we are about to also announce Zing support on Azure. We do have a partnership with Microsoft. It is not for Zing, it's for Zulu, our other JVM. But it's a natural fit now that Linux is running on Azure more and more every day to actually put Zing up there too. And then we're finding a very strong home for Zing in the data tier, specifically in the NoSQL databases whose goal is performance. The leader in that category for us is Cassandra right now, with Spark on top for queries. So Cassandra is multi-node cluster database meant to be tolerant to network outages and disk failures and all the other good stuff, but it actually can scale to larger nodes and more data if you have a JVM that can keep up with the transaction rates. So Cassandra is actually very popular right now for us. And then the JBoss data grids are popular for our caching strategies. JBoss is actually certified Zing as an available JVM, so that's nice to have another vendor say, yes, we not only support this JVM, but we endorse it, we certify it. And then just for anybody that's interested in our open source free Zulu, that is something we've been doing for about almost 2 years now. We have free downloads for Windows, for Mac, for Linux, but we're now taking Zulu into another area, and that's using it in embedded work. Same way that Oracle is already there with Java Micro Edition and Java Standard Edition embedded, now we're taking Zulu into that area as well. We just announced our very first ARM builds, so ARM processors, same stuff that's in your iPhones, and Android phones, and so that's yet another chip in addition to Intel that we can support. And we've also got Intel Edison, the little teeny wearables that Intel's making. We did our first JVM for that a couple months ago, and so those are downloadable evals. And then back to the origin of Zulu, why did we ever start building a regular old OpenJDK? It's because Microsoft wanted it for Azure. They wanted to have Java in the cloud. They didn't really want to pay Oracle or IBM or Red Hat, so they found the fourth JVM vendor. And so we supplied them a certified build of OpenJDK, and that's what's in, if you install Eclipse on Azure and you then hook in the Azure SDK, you now have got Zulu in the box, because that's the target JVM for Eclipse workbenches on Azure. And I mean, Zulu itself is a whole interesting topic. I've got a couple different examples of what Microsoft is doing, what some of the other software vendors are doing with Zulu in the cloud. And so the cloud is where Zing and Zulu kind of push-pull, or yin and yang. Embedded, we're seeing straight Zulu. Just give me Java Standard Edition so I can code in Java. I'm happy. So that's another interesting area for us as a JVM vendor to play. That's very, very fresh and very new. So that's it. If you're interested, we'll be here for the rest of the night. I thank you guys for sticking with us. I was going to ask a question. I didn't have time to update the slide. I don't have to change the question. If you do anything, go look at JHiccup and look at your own latencies and get an idea for your outliers. At least now you'll be armed with the knowledge that we shared about what latencies look like, what a latency spectrum looks like. And if you're combating latency issues, then by all means, see if you want to set up an eval to look at, or a pilot with our Zing field team. And then lastly, I got to figure out what to do tomorrow. I don't think Six Flags is open yet, but Stone Mountain was the other thing I thought was cool. My other question is, given the choice between the Coke Museum and the aquarium, which one? Okay, that was easy. Now I throw in the last one. CNN tour? Worth it? Okay, that's what I'm doing tomorrow morning.
You do it early. You see both.
Okay, do both? Okay, great. I haven't changed my return yet. So anyway, thanks. If any questions, now's the time. Otherwise, I give it back to Gunnar.
There's Zing and more Zing. Once you got it, do you have everything, or
Yeah.
you pay more for
No. The subscription model is basically how many servers for how many years, and you get every release and every feature, and there's no upsell, upcharge. If you want to buy time for an engineer, we have consulting packages. We have the quick start. We have a specific thing for Cassandra if that's what you want to do. But mostly it's, I've got 50 servers and I want a 3-year subscription, and figure out, what that price is, and off you go. Like I said earlier, it's Intel 64-bit chips, stock Linux from any of the major distros. We also can do the real-time Linux, not the embedded RTOSes, but like the Red Hat MRG or the Scientific Linux, the things that have the, I can't remember the name, but the real-time thread clocks. And some of our best latency measurements have actually come off of those, so it's pretty interesting. We're always coming out with new releases. We do about 3 major Zing releases a year, and we'll do patch releases almost once a month now. We're banging those out. And we've got, like I said, a sales rep here in Atlanta that can help you guys with any discussions if you want. I have some cards if anybody wants to take one. I didn't set them out, but if you're interested, by all means, follow up. Azul.com is our website. You'll see a whole big area about Zing. You'll probably see even the calendars with times I've given this talk. But we do go to trade shows. We did want to come to DevNexus this year. We will probably be here next February. Just when we were planning the year, we're like, we're too late. So hopefully we'll get here. But I was serious. If this group is interested in garbage collection itself as a topic, if you're interested in what we're doing in Zulu Embedded, I've got 3 or 4 other talks. I'll come back. It's fun to come down here. I get to see my sister. She lives in Milton, so not too far. All right. Thanks.